Okay, welcome everybody. What we're going to do today is take a look at the analysis process using finite element analysis. In this case, we're going to be taking a look at the helicopter pitch arm. So let's go ahead and get started. First thing we want to know is that the analysis process is more than just finite element analysis. And finite element analysis is not just button pushing. It's a tool, like a calculator. And these are the different aspects that are involved in the whole analysis process that could use finite element analysis but does not need to. So the thing we start with first is everything we do before the actual analysis. That's the pre-analysis. So in this case we have the problem statement, assumptions, and the problem approach. And this is the section that we're going to take a look at today in this video. Following the pre-analysis, after you do all that work beforehand to see how you want to approach the problem, then you go ahead and start constructing the model if you choose to use finite element analysis. And this involves a lot of steps such as preparing the geometry, making the mesh, applying the loads and the constraints, and things like that. Once that's ready to go, then we go ahead and move on to the actual processing, which is when you click Get Solve. And then after that, then we start to check to see, was this performed correctly? That's what the validation step is. And after the validation, and we're certain that it was performed according to how we planned, then we go ahead and take a look at the results and see how do these results address our problem statement at the very beginning. Okay, let's go ahead and move on to the next slide. This example of the helicopter pitch arm is actually taken from an Ansys Innovation Course, part of the stress analysis and solid mechanics. So the geometry is taken from that, as well as the loads are inspired by that analysis or by that course. And then I also found that we have, a topology optimization of a helicopter pitch arm journal paper that seems to use the same geometry and has very similar loading. So these are the references. I want to say that this is not, I didn't come up with this completely on my own. We're just using this material and putting this in the construct of looking at how to perform an analysis process. Okay, let's go to the next slide here. Looking at pre-analysis, what we do before we even open up finite element analysis. We have three main parts. The first part is the problem statement, and the problem statement is where we have the big question and the big purpose of the analysis, right? We're not doing this just to do things. We usually need, we always need some type of question to answer. There's a reason for doing the analysis. So that's the problem statement. After we have the problem statement, then we go ahead and take a look at our assumptions. Do we need to model the whole planet Earth? Or can we reduce it to something more manageable? And so this is where we try to limit the scope of the problem so that we can actually solve something and still obtain meaningful results. And once that's done, then we go ahead and take a look at the approach to our problem, which we look at the simplest possible method to address the problem statement and gain meaningful results. An important thing to know here is that we may not even need to use computational tools, including that finite element analysis, but if it does include finite element analysis, then we have to think about what is the modeling approach that we're going to use. Should we use beam elements, shell elements? Do we need to have a dynamic analysis, or can we get by with a quasi-static analysis? These are all the types of questions that we'll use and we'll think about before we even open up finite element analysis. Okay, so now we're going to go ahead and take a look at the helicopter pitch arm. And here we have an example of, there we go, a problem statement, right? We're not just analyzing a helicopter pitch arm, we're looking to redesign a helicopter pitch arm for lighter weight. And so we might have a picture in the problem statement showing the component in use here on the left-hand side and showing the actual component itself here on the right-hand side, slightly reoriented. And this will be included in the problem statement. This image is actually taken from both of those resources I mentioned earlier, both the Topology Optimization paper and the Ansys Innovation Course. And down here, we go ahead and restate the problem statement. We want to reduce the mass without affecting the peak stress. So that's our problem statement. Now the next slide is actually a continuation of that problem statement where we start looking at what type of environment this helicopter pitch arm is exposed to. And so in this case, we have lift from the blades, applying a 1,000 Newton lift and 1,000 Newton centripetal force and 400 Newton lift force. Now, these loads may not be realistic. These were taken from the paper and from the Ansys Innovation Course, but I'm trying to tie it into an explanation of what environment this might be subject to. Okay, so we might have these types of loads there. Maybe we can go ahead and use this rod there that could act as a support, and maybe there's the pitch control, that's that vertical rod here. Maybe that transfers 1,000 newtons to the pitch arm as well. Okay, so maybe that's the environment that this is subject to. Okay, so now that might complete our problem statement. With that, we can go ahead and take a look at the next section, which is what assumptions can we use and what is the approach we want to use to solve this analysis. So we'll go ahead and start with our assumptions. One major assumption is we hope that the problem statement actually presents us with a loading environment that envelopes the total environment that this helicopter pitch arm might be subject to. Okay? Because if it doesn't, then our analysis is almost meaningless because there might be a worst case load that will totally break it. Okay, we're also going to go ahead and assume that we only need to model the pitch arm and we do not need to model the helicopter, the pilot, the air, all that other stuff. Just the pitch arm. We're going to go ahead and assume that the stress concentrations are relevant. Now, I only mention that because for static analyses or quasi-static analyses with ductile materials, it could be that you can neglect stress concentrations because it will create sort of this minimal yielding region which would sort of dilute the stress concentration. But since this is in a dynamic situation, we're going to go ahead and include the stress concentrations. And we're also going to go ahead and limit the scope of this analysis to changing the geometry. So we're going to go ahead and assume that the material must remain constant. So these are the assumptions going into our analysis, and with that we can start discussing the approach that we want to use. So in this case, the part's not easily seen. I'm going to see if I can move my video here. There we go. Now you can see the whole line. We're going to assume that FEA is necessary because the part's a little bit complex. The loading and the constraints are a little bit complex to just use mechanics and materials calculations. So we'll go ahead and use finite element analysis. And we're also going to make sure that we look at the stresses not affected by boundary conditions. And this is important because boundary conditions are an assumption, right? We're not actually modeling the helicopter, we're not actually modeling the connection, and if we were, we probably wouldn't be modeling it very accurately. So the stresses in those regions are very suspect. So we're only going to go look at the regions that are unaffected by the boundary conditions. And when we go ahead and take a look at the low stress regions, we'll consider those for removal because those will have minimal impact on the load path for the part. Okay, and this process takes care of the pre-analysis step of the total analysis process, the total FEA workflow. And after this, we would go ahead and move on to pre-processing. And that is for another video. Thank you very much.